like that's working. Hopefully it won't cut out. So what we want to talk about the first day here is the synthesis of aldehydes and ketones. Collectively known as carbonyl compounds. The carbonyl group is a carbon-oxygen double bond with either two R groups, carbons, or one R group and a hydrogen. If there's a heteroatom like nitrogen or oxygen or chlorine or something else with a lone pair attached, it's referred to as a carboxyl group. So chapters 17 and 18 are about the carbonyl group, aldehydes and ketones. Chapters 19 and 20 are about the carboxyl group, carboxylic acids, amides, esters, etc. So you should already know some methods for synthesizing the carbonyl compounds because we talked about them last semester. So my first question for you is, what methods do you already know that will allow you to synthesize a aldehyde or a ketone, and from what other functional group? And the main thing we want to worry about in organic chemistry is transforming one functional group into another through some kind of reaction. So, somebody tell me a method for synthesizing carbonyl groups that you already know.
Oxidation from alcohols.
So oxidation of alcohols. That was the first one we introduced. And the product will be different if it's a primary alcohol versus a secondary alcohol. So the primary alcohol can be an aldehyde, and the secondary alcohol is going to be a ketone. And you can't make them from tertiary alcohols. Because the tertiary alcohol doesn't have a hydrogen on the carbon, which means there's no hydrogen that can be removed. In both cases here, we're going to be using the definition of oxidation of removal of two hydrogens. In general chemistry, we define oxidation as loss of electrons, but then last semester in organic chemistry, we redefined it as either the loss of hydrogens or addition of oxygen. In this case, it would be loss of hydrogen. So what reagent can we use to convert a primary alcohol to an aldehyde?
PCC.
PCC. Usually the solvent for PCC is dichloromethane. It's a good solvent, dissolves it. So what is PCC? What does it look like?
Pyridium chlorochromate.
So it's pyridium. So the pyridinium ion is the conjugate acid of pyridine, which is the 6-membered ring with one nitrogen in it. And then chlorochromate. So what we have is we have that complex with chromium trioxide. And then also complex with a chloride ion. So the business part of the oxidation is this chromium-6 reagent, chromic anhydride or chromium trioxide or chromium-6 oxide. You make this by mixing pyridine, hydrochloric acid, and chromium trioxide. And if you add them in the right order, they go to ignite. And it's a nice reddish powder that you can buy from Aldehydes. So this is a chromium-6 oxidation. And all of the oxidations we covered last semester were chromium-6 oxidations. What about secondary alcohols to a ketone? Obviously, you can still use PCC, or I don't know what, is PCC what Dr. Pistner used? Is that the reagent they use in Klein? Because there's another reagent closely related to this called PDC, which is pyridine dichromate. It is simply the pyridine salt of dichroic acid. So it's CR207 as the does the same thing. The essential part of this that makes it soluble in the organic solvent is the pyridinium ion instead of an alkali metal ion. So that's organic soluble and drags the chromium piece, the chromium 6 piece, into the organic solvent. So PCC and PDC are interchangeable. PDC is a little less acidic than PCC. So if you have a functional group somewhere else in the molecule that's very acid sensitive, sometimes PDC is a better choice. But they're functionally equivalent for your purposes. So either of those two reagents will also convert secondary alcohols to ketones. But there's another reagent that's cheaper and less toxic and easier to dispose of that will convert secondary alcohols to ketones that doesn't work for primary alcohols. What's that one?
Potassium dichromate.
So the same dichromate, but with potassium and what solvent?
Same solvent
Nope.
as the last one.
The potassium dichromate.
Oh no, it's an H2SO4 in water.
So this is an aqueous system. Because the secondary alcohol is often not soluble, it's actually pretty common to have acetone in here as a co-solvent. Because acetone is miscible with water and tends to dissolve the hydrocarbons of the secondary alcohols. And this reagent, potassium dichromate in sulfuric acid and water and acetone, is referred to as the Jones reagent. And I think that's the one that Klein introduces for converting secondary alcohols to ketones. So potassium dichromate in aqueous acid works very well for secondary alcohols to ketones. PCC is necessary for primary alcohols to aldehydes. Why? What happens if we try to do a primary alcohol with potassium dichromate?
It over-oxidizes the primary alcohol.
So if we use this aqueous acid system, it over-oxidizes. That's a nice word. What does it over-oxidize to?
Carboxylic acid.
Carboxylic. So in this case, you oxidize by removing two hydrogens to form the aldehyde, but then the aldehyde is itself oxidized by addition of another oxygen to the carboxylic acid. Does anybody remember why that over-oxidation occurs?
I think it's the position of the alcohol, like the fact that it's primary.
So the primary alcohol gets oxidized with K2CO207. Right? And it does it by making a chromate ester. And then that chromate ester can do E2 elimination to form the aldehyde. And the chromium species, right, that is now a reduced chromium species. But then it doesn't stop. The aldehyde is actually more readily oxidized by this aqueous acid system than is the primary alcohol. So yes, it's because of primary alcohol, but why is it that the aqueous acid system oxidizes the aldehyde, whereas the non-aqueous kind of neutral systems don't? What does the aldehyde do in the presence of aqueous acid? It's perfectly fine, by the way, for people whose name is not Isabel to answer questions. Or you can just make her answer all of them, I guess. So I covered this in my class. Dr. Pfister probably didn't. Go ahead.
I think it has pKa.
It actually is not related to the pKa because it's chromic acid that's doing the oxidizing.
Mine.
It has to do with what the aldehyde will do in the presence of aqueous acid that it won't do in the absence of aqueous acid. And
Oh, does it become an ion?
Not quite, but it does react with aqueous acid. And it reacts with aqueous acid to form a hydrate. And I covered the mechanism for the hydrate formation in one of the next set of videos. So what will happen is you'll protonate this carbonyl group, and once you've protonated that carbonyl group, you've got a very electrophilic carbon here. It already has a partial positive charge on it, and if you protonate the carbonyl group, then it has a full formal positive charge on it. Water will then react with that positive charge. So you get this hydrate. This hydrate now looks like an alcohol. So there's nothing to stop this hydrate from eliminating two hydrogen atoms. The fact that this is an OH group here rather than an H group doesn't affect what chromic anhydride is going to do to it. It really doesn't care if this OH group is here. It just sees a hydroxyl group and a hydrogen attached to the same carbon, forms a chromate ester, and then does that E2 elimination. Hydrate formation has to be suppressed if you're going to avoid overoxidation. And the way to suppress hydrate formation is to not have acid and not have water, right? Which is why we went to a non-aqueous system. And then we had to change the counterion from potassium to pyridinium to make it soluble. And then we eliminated the water so we don't get that nucleophilic attack. So overoxidation is a consequence of this nucleophilic acyl addition reaction to the carbonyl group in the presence of aqueous acid. So we've got good reagents for converting alcohols to carbonyl compounds. And depending on the structure of the alcohol, we'll get different carbonyl compounds. Am I correct in the assumption that Dr. Pisker did not talk about the mechanism of overoxidation? He usually doesn't.
Your OS is not stable.
What's that?
Your OS is not stable.
Yeah.
Your OS.
Yeah, it's not stable, but it's not stable because it forms the hydrate. So what is the other method that we learned last semester? We actually learned two other methods.
Alkenes to aldehydes and ketones.
So alkenes, carbonyl compounds, using what reagent? Checking the time here. I think I actually fixed it. Nope, it's 9:15 on the clock, and it's 9:45 on the computer, so they didn't fix the clock. So what's the reagent that allows us to convert alkenes to carbonyls? And it will depend on the type of alkene. A mono-substituted alkene will lead to the aldehyde, and a di-substituted alkene will lead to the ketone. So if, for example, I have an alkene that's mono-substituted on this end and di-substituted on that end, when I oxidize that up, I'll get a ketone for the di-substituted end. And an aldehyde for the monosubstituted end. So what if I were to give you this question? on next Tuesday's quiz and ask you to fill in the reagents above that arrow. What are you going to stick in
Is
there?
it a 3 and CH2Cl on the top?
So it's ozonolysis. The solvent for that is also usually dichloromethane. Ozone is blue when dissolved in dichloromethane. So this reaction tells you it's done by turning blue when the reaction is complete. When there's no more alkene for the ozone to react with, it will just dissolve and turn blue, so you know it's done. Very easy reaction. After it turns blue, you just bubble nitrogen through it until there's no more blue color, which means the ozone is gone, and then you wrote it back. Very clean. But that's not the only thing. That doesn't actually make this directly. What that does is make an ozonide, which is a tri-membered ring. Right over carbon. Add it. So it makes this ozonide, which looks a little bit like a fox. And then the ozonide has to be treated with something to generate the aldehyde ketone. Go ahead.
I think your voice keeps cutting out, but would it just be a reducing agent like zinc or acetic acid?
Zinc or acetic acid is one possibility. My voice may cut out when I turn away from the microphone. I'm trying to walk near it when I'm talking. So zinc and acetic acid, and then the other product will be zinc oxide. The zinc basically takes one of those oxygens out. And there's another, these are mildly reducing. If you work it up with a strongly reducing reagent, like sodium borohydride, you can actually get alcohols out instead. So you would get a secondary alcohol here and a primary alcohol there by working out with a strong reducing agent. You can also work these up with an oxidizing agent. If you work it up with hydrogen peroxide instead of the zinc and acetic acid, you'll get a carboxylic acid on the end, so effectively over-oxidation. What's the other reagent, the more common one that we use?
CH3, CH3.
So dimethyl sulfide. And if you use dimethyl sulfide, which is sometimes abbreviated DMS, if you use that, the other product is dimethyl sulfoxide, DMSO. Right? And it does the same thing. It basically lassos out one of these oxygens. The oxygen-oxygen bond is always pretty unstable. So either of those two mildly reducing workups will allow you to convert the ozonide to the aldehyde and the ketone. So that's method 2.
Nice.
Say that again. I missed that.
We couldn't hear you at all for that.
You couldn't hear me at all for that? Well, I don't know why that's the case. You can hear me now, right?
It sounds your internet is not stable. Maybe you can try to use the wired connection.
I have a wired connection.
Okay.
I have a wired connection with almost a 200 megabit per second upload speed. So that should not be the problem. I'll do a quick speed test here and make sure that it hasn't gone to shit. Yeah, yeah. I still have a really good internet connection. It's even a little bit better than it was. Yeah, 215 is plenty. Discord usually lets me know if there's an unstable connection, and it has not been letting me know that there's an unstable connection. So that shouldn't be the problem. Maybe the way the mic is configured. I have it sitting on the desk here. It's clear now, right? And it could just be...
Not very.
Really? Huh. Okay. Let me just check my microphone settings. Is there anybody who's yeah, that's fine. Is there anybody who's not having trouble? Because it could be on your end too.
Hearing okay right now.
Yeah.
But sometimes when you go to the board, I think it's picking up the chalk hitting the board more than it's picking up your voice.
You know, one of the things you hear a kind of a dull roar in the background. It's really picking up the air handling system, and the air handling system is particularly loud this morning. And I don't have a solution to that problem. I mean, I have the mic.
It'll be fine for the first 5 minutes, and then once we're on a roll, then it'll just cut out for 30 seconds for me, and then you'll be back.
Yeah. I can't really get the mic anywhere closer to the board because it's perched on the front desk. And it's not giving me any error messages. It's unfortunate. So all you missed was my summary of saying that we have the way of converting the alkenes to aldehydes and ketones using ozonolysis with a mildly reducing workup. And we have two choices for mildly reducing workup, either dimethyl sulfide or zinc and acetic acid that will allow us to go there. But we could also, if we wanted to, make alcohols and carboxylic acids by changing that second step. First step's the same, ozone and dichlor method. So we've got two methods so far: oxidation of aldehydes and ketones, oxidation of primary and secondary alcohols to aldehydes and ketones respectively, and ozonolysis of alkenes to give aldehydes or ketones depending on the substitution on the alkenes. What about the third method that we learned last semester? What other functional group can we convert the
Alkynes, hydration of alkynes to aldehydes and ketones.
So hydration of alkynes is the other one. And if it's a terminal alkyne, that will generate an aldehyde. Or an anti-Markovnic oxidation. Or a ketone from Markovnic oxidation. Frankly, the mic problems may just be a combination of the noise from the air handling system and me having mask on and having to face the board. And if it's an internal alkyne, we get ketones, and usually a mixture of ketones. If it's unsymmetrical, we'll get two different ketones because we won't be able to control which direction that hydration occurs. So hydration of alkynes is most useful when you're working with a terminal alkyne. So what are the reagents for Markovnikov addition and for anti-Markovnikov addition of an alkyne? And as an example, let's just pick propyne, the simplest possible terminal alkyne. So we can convert that into the aldehyde if we want to. But we can also convert that into ketone. And you should be able to fill in the reagents.
For the anti one, it's like a boron complex. It's like the boron with the two cyclohexanes and the hydrogen with a complex with THF.
So it's dicyclohexylborane. And it's not actually complex with THF. Regular borane, BH3, is not stable. And so you buy it as a complex with THF. Dicyclohexylborane is actually a stable compound. So it's usually run in a solvent of either ether or THF.
The THF is the solvent for this one.
Right. It's going to be an ether solvent, ether THF. Those work well. So that's the first step. That's the hydroborane.
Yeah, the second step is hydrogen peroxide and I think NaOH.
Yeah, basic hydrogen peroxide. So the product of the first step is just the hydroboration. So after step 1, what we get is an alkenyl borane. You'll notice that the boron and the hydrogen are on the same side. So this was a syn addition here. Because it goes to a four-membered ring transition state, it's a concerted mechanism. And then the second step converts that boron complex, or boron compound, that alkenyl borane, to the aldehyde. And the mechanism for that is in the pre-recorded videos, if you don't remember it. So that works. Is that the reagent that Dr. Kushner used? Is that the reagent Klein uses? Because there's another common reagent that does this same transformation, and some books use that one instead.
I was in Pistner's last semester, and I remember the THF and the hydrogen peroxide, but I don't remember the boron complex.
So he may have used a different boron compound called 9BDN.
Yep, that's the one.
Which is 9-borobicyclononane. So the abbreviation comes from borobicyclononane. It's very similar. It's a boron that has one hydrogen attached to it. And then it has this kind of double chair cyclohexane. You could redraw this if you wanted to. Looking like that. Boron bridging across. Right, so you've got two cyclohexane rings kind of leaning on each other. It's numbered like this. So it's 9-borobicyclo because it's atom number 9 is replaced with boron. The essential components of this is that we have large, bulky alkyl groups replacing two of the hydrogens on the borane. So we have only one hydrogen, and because we have only one hydrogen, it can only add to one equivalent of alkene. We can't add another, or alkyne, sorry. We can't add another molecule of alkyne across that same boron. And because it's hindered, it's not likely that two borons are going to add to the same alkyne. We don't really want another boron adding to this alkene. So putting steric hindrance on here limits the reactivity of this carbon to attack another boron. So we get a 1-to-1 stoichiometry instead of the other possibilities. So 9-borobicyclononane is kind of a pain in the ass to draw. So often it's abbreviated by showing this like a little parachute. So a kind of shorthand for 9-ppm is that little parachute on there. So 9-ppm and dicyclohexylborane will do exactly the same thing. But I think Klein uses 9-ppm and Volhard and Shore uses dicyclohexylborane. What are the reagents for the Markovnikov addition?
H2SO4 and H2SO4.
So mercury 2 sulfate, mercuric sulfate. And aqueous acid. So it's catalyzed by the mercury 2 ion. It's similar mechanistically to the oxymercuration, except that we only need catalytic quantities of the mercury 2 sulfate, and we don't have to have a demercuration step because the mercury falls off spontaneously. Both of these go through a keto-enol tautomerism at the end. So we initially hydrate to form the enol, but then the enol is unstable and tautomerizes to form the more stable carbon-oxygen double bond. So those are the three methods that you learned last semester. And at this point, I'm going to take about a 10-minute break, give you guys a chance to rest, and then we'll introduce the new methods that are new this semester. Are there questions before we take a little bit of a break? Does this class end at 10 o'clock or 10:10? Last semester, I know there were 8:20 to 10:10 classes, but I got an email from the provost earlier this semester talking about an 8:20 to 10 o'clock class. So I'm wondering if they changed that.
I feel like on my self-service account it says 10:10.
Okay.
I'm actually 10:10 too.
Okay. So I think that was probably a typo in the provost's email or just an innocent mistake. Okay. So what I'll usually plan to do is we'll have a quiz and then I'll lecture for 40 minutes or so, and then somewhere around 9 o'clock or 10 after 9 we'll take a 10-minute break to give you guys a chance to catch your breath, and then we'll come back. So normally what people do during this break is go down and get muffins at the Ritaza cart, but you'll have to get your own muffin today. And this will also allow me to stop the video recording so we don't have a huge long video, and I'll save it while we're taking our break. Anything else before we break?
Said you'd post the videos, right?
I will be posting the videos. I'm not sure how promptly, but yes.
Okay, I just missed part of what you wrote down for something, so that's it.
That's fine. All right, I'm going to stop.